Mixtures and Solutions, Part 3, the Solvation Process. Here we're going to apply a submicroscopic model to explain how aqueous solutions form with ionic solutes and how they form with molecular solutes. Let's take a look at how it is exactly that solutions form. For a solution to form, the solute particles must be separated and pulled apart from one another to mix evenly among the solvent particles. This means we'll need to focus on the interparticle forces, the attractive forces, between the solute particles themselves, between the solvent particles themselves, and between the solute and solvent particles together. For dissolving to occur, the solute particles must be completely surrounded by solvent particles. That means the solution will have to overcome the attractive forces between the solute and other solute particles, and between the solvent and other solvent particles. Then, new attractive forces will be formed between the solute particles and the solvent particles. The process of surrounding solute particles with solvent particles to form a solution is called solvation. Solvation that occurs in water is known as hydration. A general rule for figuring out whether or not something is soluble is called like dissolves like. It means that if you were to consider the kinds of interparticle forces within the solute and within the solvent, if they're similar, then they tend to dissolve. If not, then they tend not to dissolve. Ionic attractions are essentially the most extreme cases of polarity, so ionic and polar solutes both tend to dissolve in polar solvents. Water is a polar solvent because there's a large electronegativity difference between the oxygen end of the molecule and the hydrogen end of the molecule. The bent shape produces a negative dipole on the oxygen end and a positive dipole on the hydrogen end. Since water is polar, we would expect to see it dissolve most ionic solutes and most polar solutes. Nonpolar solutes will not dissolve in polar solvents, but are soluble in other nonpolar solvents because they have similar interparticle forces. The solvation process for dissolving an ionic solute, like sodium chloride in water, is shown here. The sodium chloride formula units will not only separate from the crystal lattice, but will also dissociate into separate individual ions of sodium and chloride. Dissociation is the process by which an ionic compound separates into its individual ions as it dissolves. The water molecules will also separate from one another to make space for the ions to dissolve. Notice how the polar water molecules align themselves around the positive and negative ions. The positive sodium ions are surrounded by the negative ends of the water molecules. The negative chloride ions are surrounded by the positive ends of the water molecules. Since each ion is fully separated from the crystal lattice and from each other, this explains why solutions are always homogeneous mixtures. Each individual ion is way too small to see, even under a microscope. So if you look at it, all you see is the solvent. Polar covalent compounds that dissolve in water follow a different process. This diagram only shows one sucrose molecule, but it is surrounded by a host of water molecules. In order for solid sucrose to dissolve, the C12H22O11 molecules would each separate from one another, and the water molecules would spread out and make room for the sucrose molecules. Then the sucrose molecules would be hydrated by the water molecules, forming new attractive forces, hydrogen bonding, between each sucrose molecule and several water molecules as shown here. Polar water molecules can form new dipole forces with water because water is also polar. Like dissolves like. Again, it is important to note that this sucrose molecule is still all together. There's no dissociation here, but it is an individual molecule, separated from all the other sucrose molecules. That's why solutions are completely homogeneous. The individual particles are surrounded each individually by solvent molecules. The overall energy change that occurs during the solvation process is called the heat of solution. Energy is required to overcome the attractive forces between the solute particles and other solute particles, especially if it's a solid. And energy is required to overcome the attractive forces between the solvent particles and other solvent particles. Both of these two processes are endothermic, because they absorb energy to overcome the attractive forces. Energy is released, however, when solute and solvent particles mix because new attractive forces are formed. This is an exothermic process. A few ionic compounds are insoluble in water, and this is because their solute-solute attractions are so much stronger than the attractions that could potentially form between the solute and the solvent particles. Similarly, nonpolar covalent compounds are insoluble in water because of their vastly different interparticle forces. Oil and water are immiscible because oil is composed mostly of hydrocarbons with nonpolar bonds and no dipoles. Thanks for watching this video that applied a submicroscopic model to explain how aqueous solutions form with ionic compounds and molecular compounds as they dissolve in water.